In this video, we're going to talk about the KVL-KCL combination. KVL stands for Kirchhoff's voltage law. KCL stands for Kirchhoff's current law. And it's another method to solve a problem without doing any kind of circuit reduction. It does require some math, but the math isn't very difficult. So we're going to get started. So we have to go through several steps. Step one is to identify the loops. Step two is identify the nodes. 3 is draw current in the node, right, going in and out of the node, and 4 is write out the voltages. From this blank sheet of paper, this is how you fill it in, okay? Number one, identify the loops. So a loop is basically, a closed circuit, right? So we have two closed areas of the circuit. One is loop 1, right? Looks like a giant square. This is loop 2. Now that's pretty obvious, right? The second is, so we've done this, okay? The second one is identify the nodes. A node is simply an intersection. Now you have two intersections, but for right now, for our extents and purposes, right, you'll do the top node right here. And we're going to label this node A. Now, even though this is a node, you really don't fill this in, and I'll explain this in another video why you don't fill this in. But for right now, we'll stick with one node, okay? And we're going to go ahead and do that. So here, we identify the nodes, okay? Then what we do is we draw the current into the identified nodes, right? So draw currents, really it's plural with nodes. So here we have our current running this way. So our current runs here, and we're going to call this current I1, and it's running in this direction, okay? So it's going to run this direction, it's going into the node, just like that, okay? Now, here, we're going to assume I2, which is over R2, is coming out of the node as such, okay? These are just assumptions, okay? And I3 is going out of the node there. So these are stuff. If it's coming in, it's going to split, it's going to come back and go back to the source. This is an assumption. If the assumption is wrong, your number will become negative and you'll just flip the direction. But for right now, we will hold these assumptions to be true. Then we write out the voltages based on the current. So the current, as the current moves across the resistor, you have VR1, right? It goes from high to low, right? As the current moves across the resistor, we have VR2. As the current moves across this resistor, we have VR3, just like that. Okay, from here, we organize or we create our equations. Now this requires a little bit of math. It looks probably a little scary if you're not used to it, but it's really very simple, and I'll explain every step. We analyze loop 1, then loop 2, then the node. Okay? And we went ahead and let's write out the voltages. So first, loop 1. Loop 1 is KVL, Kirchhoff's voltage law, and we got to use a sign convention, right? So what sign convention do you want to use? Normally, I tend to favor the second sign convention. So as the current moves this way, this is the first sign, this is the second sign. First sign, second sign, first sign, second sign, just like that. And so we write second sign. So now you're communicating with me how I derive this formula. Okay? So then, what you want to do is you write out this, and this is kind of an optional part. I tend to write this out, but you don't have to. I mean, some of the volts going counterclockwise or clockwise, right? We're going clockwise. This is the clock. It's going clockwise is equal to 0. So I'm going to travel clockwise around the loop. Clockwise. So as I travel clockwise, positive Vs. Travel clockwise, negative VR1. I travel clockwise, minus VR2 is equal to 0. Okay? Now, what do I do? Well, from here, what's my Vs value? Well, my Vs value is 10. Well, that was easy, right? 10. What's my VR1? I don't know. I don't know what that is. What's my VR2? I do not know. And that's equal to 0. Fair enough, okay? If I don't know something, then this is going to be IR, because V is equal to IR. So remember that. If you don't know it, it defaults to IR. So now that's 10 minus IR, but what I is VR1? It's I1, R1. Minus I2, R2. is equal to 0. R1 is 10, R2 is 5. 10 minus R1, right? And I plug in R2, which is 5 up here, so that's 5. Okay? Now, I'm going to do a little shortcut. I'm going to give you the answer. Okay? So here, if you draw down the algebra, what's the answer? The answer is 10I1 plus 5I2 is equal to 10, and you can reduce this to 2I1, I2 is equal to 2, right? If you want to really do that. But we don't have to do that. But I want to show you here how I derived it. So what I'm going to do is I'm going to make a little bracket here, and I'm going to show you how I derived this equation. 10 minus I1 times 10 minus I3 times 5. I'm sorry, it's I2 times 5. Erase that. Is equal to 0. Minus I1 times 10 minus I3 times 5 is equal to 0. So what happens I'm sorry, it's equal to 10 minus 10, right? Because the 10 comes to this side, so the positive 10, when it comes to this side, it becomes minus. And then you multiply it by negative, you get what? 10I1 plus, by the way, this is I2, I apologize. It's going to become a force of habit. 5I2 is equal to 10, and that's how we get that, right? Now I can reduce this further, but it's really not necessary. Okay. Then what I want to do is loop 2, and I'll draw a line right here just to kind of keep things separated a little bit because it's going to get a little longer than anticipated. So I'm going to move this up, loop 2, and then we're going to use, in the loop, it's KVL. KVL, I'm going to adopt the second sign, right? And so as I travel across the circuit, okay, I'm going to write out KVL here, and I'm going to write out sum of the volts around the loop is equal to 0. So as I travel clockwise around the loop is equal to 0. So let's do the second sign convention as we'd indicated, right? As I travel clockwise is here, plus, and I'll put a little star behind it or put a dash behind it to indicate this is the second one. Circle, and then circle. I come this way, circle. So I have plus VR2, right? Just like that. And then I have minus VR3. Just like that. That's equal to 0. Okay. Now, what is my value of VR2? Right? I don't know. So I'm going to put question mark. What's my value of VR3? I don't know. I have no idea. Okay. So I'll take my VR2 and I type in I2, R2. Just like that. I2, R2. What is my VR3? Right? It's going to be I3, R3. Minus, equal to 0. Okay? I plug it just like that. Apologize, right? So you didn't see it. I2, R2, I3, R3. So as I scroll back up, I need the value for R2 and R3. Where's R2 and R3 coming from? R2 is 5, R3 is 5. So it's 5. Yeah. So it's 5I2 minus 5I3 is equal to 0. Therefore, what? I2 minus I3 is equal to 0, which is I2 is equal to I3. Right? Straightforward. Okay. Now, we have one more equation. So this is one equation from our loop 1. This is our second equation. That's loop 2. And then we have our node. We have to get our nodes. So our node A. And inside node A, we have something called KCL, Kirchhoff's current law. So you have loop, loop, node. Okay? So how do we solve this problem? Well, we simply we write out what is Kirchhoff's current law. Kirchhoff's current law states some of the currents coming into a node is positive. So this is a current coming into a node, it's positive, and its sum is 0. Okay, what does that mean? That means that is I1 coming in or out of the node? Is going into the node, so it's I1 positive. Is I2 going in out of the node? It's going out, so it's negative I2. Is I3 going in and out of the node? It's going out, so it's minus I3 is equal to 0. So I1 is equal to I2 plus I3. These are three equations. Okay, so from here you're deriving these three equations, here, here, and here. Now there's several ways to solve for it. I'm not going to solve for it in this video. I will solve for it in the next video, and I'll solve it a couple of different ways. But for right now, if you can derive this, it's pretty much most of the problem. Okay. In the next video, I will show you how to use the computer to get the solutions and handle this. Okay.